My name is Vincent Guittot. I'm working for ST-Ericsson as an embedded Linux engineer. And I have been assigned to the Linear Power Management Working Group. And as a member of this working group, I have studied if it was possible to use the regular scheduler in order to reach the same behavior than the CPU hotplug. And so the purpose of this presentation is to describe why we are using the CPU hotplug, or why we have used the CPU hotplug on ARM embedded system in order to make some power management. So after describing my environment of test, I will give you some first figures, but I will also point out some constraints linked to the use of CPU hotplug. And then I will start to explain which kind of behavior we really want in embedded ARM platform and how we can reach such behavior. So I will finalize with some open issue and the limitation with the current implementation of the scheduler before concluding. So why to use CPU hotplug framework for doing some power saving? The first and main reason for using the CPU hotplug on the dual Cortex A9 platform was that some CPU idle driver only managed the CPU 0. And in SMP mode, so when both CPU was plugged, the WFI, so the wait for interrupt state, which is not a real power level state, was the only reachable state. And the CPU 1 had to be unplugged in order to be able to reach the deep C state, so which was the retention state or the power off mode of the cluster. So the main advantage of such driver was their simplicity, in addition to the fact that they were quite similar to the driver that was used for any processor system. The main drawback was that we have no real power saving when both CPU was plugged. So for the high CPU load use case or the mid-range CPU load use case, when both CPU were necessary, we were doing no power saving. So now most of the CPU idle driver are managing or are going to manage the SMP mode. So this means that the deep C state of the cluster can be reached even when we have both CPU running simultaneously, and we are able to reach the same power consumption level than when we unplugged the CPU 1. But this management have implied the synchronization of the idle state of each core in order to be able to choose the final power state of the cluster. So as a result, we have some more complex enter and leave idle sequence, because when one core is entering an idle state, he must check and wait the other core to be idle also in order to put the complete cluster in retention or off mode. So nevertheless, even if we have now some SMP CPU idle driver, the CPU hotplug still does better when we speak about the power consumption of some use case. So we generally have a better retention rate. We generally have less transition between idle state and running state. And at the end, we have a better power consumption at the battery level. So these three assumptions are only available for aggressive low power use case. So I mean such use case which have light CPU load and which doesn't take any benefit of the SMP effect. So the fact that we can have several CPU running simultaneously. So as they don't take advantage of such behavior, we still have a gain to use the CPU hotplug. Okay. As an example, so for such low power use case, we speak about low power MP3 playback or the voice call use case in which the screen is off and there is no real user interaction. So I have done a quick test with a linear Android build, so the 12.1 version. This version is not an optimized software. It's mainly used to make some demonstration and to demonstrate what we are doing in linear. And the power consumption at the battery level is quite high. But that's not a real issue for me because I don't want to measure the complete power consumption, but only the power consumption of the ARM cluster. So the fact that some device are maybe not powered down is not a real issue because they are not used for what I want to do. So I have done some measurement of on my Snowball board while I was playing an MP3 file. So the screen was off in order to minimize the user interaction and the graphic activity. And I have measured the power consumption in both SMP mode, so with a regular SMP driver, CPU idle driver, and when I unplug the CPU one. So the results, which are displayed on the screen, show that we have something like 10% of gain when we are unplugging a CPU one compared to using the normal regular scheduler behavior. And this result is aligned with the cluster state statistics. So in fact, we see that when we unplug the CPU one, the time spent by the cluster, the dual Cortex NF cluster in a retention state is higher. So we have 4% of difference, which is in fact aligned with the the power consumption of the cluster. So for this use case, the CPU one was not power gated, which is possible on some ARM platform. It was just in WFI. It was just waiting for the other CPU to go in a deep sea state. I have done the similar measurement on a Panda board, which is also a dual Cortex A9 platform. And I've been able to measure the power consumption on the VDD Core 1 power rail. So I don't know exactly which part is linked to the ARM on this power rail. But nevertheless, we can see that we have an improvement when we are unplugging a CPU compared to the SMP, compared to a SMP CPU idle driver. So the main outcome of this measurement is that the power consumption is still better when we are unplugging a CPU compared to the normal SMP behavior. And the goal of this presentation is to describe what makes this difference and how we can remove this difference. So I'm going to make a quick description on my environment because I have not used the MP3 playback to do all my tests. So in fact, in order to study this power consumption difference, I have used the cyclic test tool. So this tool is quite simple. It's created a defined number of threads which are using a high resolution timer in order to wake up periodically. It also gives some statistics about the latency of the system. Such behavior can be used to simulate some multi-threaded use case and some light CPU load use case, which is exactly what we want. And with cyclic test, we have some advantage among with the test can be easily reproduced. So when we have this, if we use the same configuration of cyclic test and we are doing measurement, we will get the same result, which is not already the case with when you have a framework like Android and so on. So with cyclic test, we have no dependency with any user framework, any optimization of this framework, or depending of the version. We have no external dependency with external device or firmware. We just rely on the kernel and its behavior. So to make simple, I have used cyclic test in order to create some threads which are waking up each 2 milliseconds. So and I'm increasing the period interval. I mean, my first thread will wake up each 2 milliseconds, the second thread will wake up each 2.5 milliseconds, and so on, in order to create a small asynchronous activity. So I have also used a specific configuration of cyclic test to be sure that I will have the same number of wake up in a given time. Because when we use only one CPU, the thread will wake up sequentially, and we can have a slight delay between the activity of this thread, which at the end may result in less wake up in a given time. So there is an option which makes sure that we will have the same wake up during a given time. So regarding the software, I have used a linear kernel 3.2 version. So it's the 3.2 kernel on which we have merged some patches which are under review. I have also used the linear developer rootfs, which is something quite simple and quite similar to an Ubuntu one. And I have added a SMP CPU idle driver, which was able to put the cluster in retention when both CPU was online. My hardware environment was a dual Cortex A9 platform, so which is the 9500 chipset from ST-Ericsson, and the Snowball board. So I have modified my Snowball board in order to be able to measure the power consumption of only the cluster, the ARM cluster, for the ARM cluster. So now that I have described my environment, we can come with the figures, with some figures. So I have displayed two main results. On the left side, we have the power consumption of the ARM cluster versus the number of threads that are running during the test. So I have started with one thread, which is running, up to 7 threads. And we can see in green that the CPU hotplug consumes less power in milliwatt than in SMP mode. So this difference is increasing. So it will not increase whatever the number of threads is. We will have a threshold above which the SMP effect will become more significant than the time wasted by any synchronization and so on. Okay, so I have not displayed all the tests with up to 20 threads, but we have an inflection point in which the SMP become quite close to the hotplug, and then we will consume less power consumption with the hotplug. Okay. On the right side, I've put some statistics about the cluster power state. So we have 3 main states, which is the running state, the WFI state, and the retention state. So the running state means that at least one CPU is running or is going to enter an idle state. The WFI is just a wait for interrupt, so it's quite a simple waiting state. And the retention state is the best power saving state for the cluster. So we can see, so the retention state is the green area, and we can see that in SMP, the retention rate is lower, and we are spending more time in WFI, so in wait for interrupt. And this difference, which is about 10%, is aligned by the fact that we have a lower power consumption with the CPU hotplug. So this result is linked to the test in which I'm using 4 threads simultaneously. Okay, so I have something like 10%. Yeah.
So what's the frequency?
Yeah. So I'm always using the lowest frequency of the platform, so it's 200 megahertz. In fact, the platform can reach 1 gigahertz, but as we are studying the low CPU load use case, the on-demand governor keeps the lowest frequency. I have made a quick test. I have used the next frequency, the 400 megahertz frequency, to see how the power consumption was. And in fact, it was not better. and it was even a slightly worse than using the lowest, just because we are increasing the voltage of the cluster, and this increase of voltage and power consumption is not compensated by the reduction of the running time. So.
And how often, what was the period of these wake-ups?
So 2 milliseconds. For the first thread, 2.1 for the next one. So when I'm using only one thread, I have one thread waking up each 2 milliseconds. When I'm using two threads, the first thread is waking up 2 milliseconds, and the second thread 2.1, 2.5 milliseconds. Cyclic test is increasing the period for each new thread. So I'm started with 2 milliseconds and a 500 microsecond step, increasing step.
What is the government policy to put the CPU1 up there?
It was just an inline command. I was unplugging the CPU1, starting my cyclic test, doing my measurement for a few seconds or minutes.
Okay, so this is not dynamic?
No. Yeah, yes, and I was manually switching from one configuration to the other one. The goal was just to compare the power consumption in either one CPU, one CPU is running only and the other one is unplugged, or when both can run. Where I'm not taking into account the policy or user governor, which could choose between using one or two CPU.
The cluster statistics is for the whole cluster of the two CPU? Or
Yes, it's the dual Cortex A9 cluster.
you cannot put retention?
No. Only we can put in retention only the complete cluster, so the dual core simultaneously, just because they are sharing some cache and some cache coherency logic. So ARM platform can purgate only the one core logic. It's possible for some platform. But in order to reduce the voltage and to make the complete cluster in retention state, we must have both CPU in idle.
So, sorry, when
Yeah.
you say 7 threads, for instance,
Yeah.
it doesn't mean that every 2 milliseconds you're having at least 7 different wake-ups?
No, I mean that I have 7 threads which are running, one with a period of 2 milliseconds, one with a period of 2.5, one with a period of 3 milliseconds, one, and etc. up to the 7th
So
thread.
they are unlikely to...
Now, they are not synchronized. They are waking up quite asynchronously. So now that we have seen that the CPU plug can give us some power consumption gain, we also need to describe the constraint. Yeah.
So what's the overhead for the CPU bottleneck when you're plugging? How much time does it take?
We will just speak about that now. It's one of the main constraints of the CPU plug. So the CPU plug has got some constraints, mainly 2 constraints. So the first one is that the CPU plug is a power-consuming sequence because we are not only updating the CPU mask, so the online mask or the present mask, but we are also resetting some memory structure which are linked to the CPU. And in addition, we have dozens of callbacks which are running each time you are plugging and unplugging the CPU, because a lot of threads or whatever are created when we are plugging the CPU. So in order to compensate this power consumption, the CPU plug must be used in a large time scale. So by large time scale, I'm more speaking about second or minute than millisecond or hundred of milliseconds. Okay. So it's clearly when you are sure that you will not need the CPU1 for a long time, you can unplug the CPU. We have another issue with the CPU plug is that it can be a time-consuming sequence. So when you are plugging a CPU, you are created some thread which will be pinned to this CPU. Okay. We have done a quick test. So we have plugged and unplugged the CPU several times, and we are increasing the CPU load step by step. So I have still used the cyclic test to doing that. So the row gives you the number of cyclic test tasks that were started and each task I've got up to 10 threads running simultaneously. So we can see that the plug sequence is quite stable, and we have, for this test, which was done on a 2635 or 38 version, we have something like 100 milliseconds for plugging a CPU. So this value is quite dependent on how many threads need to be created. So if you have enable all the CPU thread governor, for example, you will create one governor for underbound, one thread for underbound, one thread for the conservative, and so on, which can delay your plug sequence. But so we have a stable value, which is around 115 milliseconds when the system is not loaded. And we have a threshold above which the CPU up duration is increasing quite linearly. And in fact, this threshold is when the CPU 0 becomes overloaded. So when we are plugging the CPU, we are creating some threads. So we need to wake up the case thread D daemon. And this daemon needs to run on CPU 0 in order to create the thread. So as the CPU is already overloaded, we are just waiting to have the CPU, in fact. That's why. So regarding that, it means that we must take care when we are plugging and unplugging a CPU, because you can have the situation where you have a huge increase of your CPU load because of a user activity. So you need to plug the CPU 1 in order to respond to this activity, but you don't have enough CPU capacity or CPU power to make that quite quickly. So the CPU plug has got some constraints, so which make this solution not so interesting for us. It has got some advantage, but it has got also a lot of constraints, which make that not easily usable in a fast manner or in a, let's say, periodic manner. So the goal is to come back on the regular scheduler and to see if we can have the same behavior when we have some low CPU load use case, so that we can have the same CPU plug power consumption without all these constraints linked to the plug and the unplug sequence. So the current SMP behavior is displayed on the screen. So this is a kernel shark screenshot. I have using kernel shark and the trace to see how the scheduler behaves. So with the current scheduler, we are using both CPU, okay, which is what we expect from an SMP scheduler. But when we have few tasks or small tasks, we can see that most of the time the CPU are not used simultaneously. So in the two green circles, the two CPU have been used, but sequentially. And we could have optimized that in using only CPU 0 and running these two tasks on the CPU 0. So that we will have minimized the inter and leave sequence, which have a power cost, and we will have no additional delay or effect on the result. So what we want for the low CPU load use case, so we want to keep the CPU 1 idle in order to let him reach the deepest possible state, C state. And we want all the small tasks on the CPU 0. So the task, but also the interruption, the timer, and the work queue. We want everything running on CPU 0 when the CPU load is quite small. So how to do that? The first point is the interrupt affinity. So the default interrupt affinity is that all the core can be used to handle an interruption. Now, when we look at the ARM interrupt controller driver, and more precisely for the set affinity function, we can see that we use the CPU mask any and something. And this macro will take the first CPU of the mask. So as we are specifying to use all the CPU, in reality, the interrupt controller will be set to use only CPU 0. So unless some specific configuration, the CPU 0 will be the one that will handle all the interruption. And that's exactly what we want for our use case. Now, if you use a daemon like ERQ balance, you must ensure that his policy, because he has some power policy, will be aligned with your behavior and will not spread some tests, some interruption on CPU 1 while you want to keep everything on CPU 0. So the next point is the scheduler and the topology. So the current ARM topology describes a multi-core single package which gives us the information that all the cores are sharing some resources like the cache and some additional things, but mainly the cache. For the scheduler, what is interesting is the fact that we are sharing the cache between our two cores. So this configuration makes the migration of tasks between the core easier than another configuration. So when a task wakes up on a busy CPU and there is an idle CPU which is sharing the cache, in this case, the scheduler will migrate this cache on the idle CPU. So this behavior is quite good for the responsiveness and for the performance because you will not wait for a CPU. But it's quite bad for what we want to do in our use case, which is keeping everything on CPU 0. So we need to modify the ARM topology in power saving mode to say that we don't want to make this migration so easy in low power use case. So the scheduler has got a power saving mode, which is called SCADMC, and which tries to gather all the tasks in a minimum number of packages. But the main problem for us is that our dual Cortex A9 cluster is only one package. We have also the load balance, and the default configuration of the load balance is that a CPU has got the capacity of one task to run simultaneously, which is quite normal, which also means that a CPU will become out of capacity and the scheduler will try to migrate some task on another CPU as soon as we have more than one task running on it. And this is not exactly what we want, because even if we have an idle CPU, we want to keep this small task on CPU 0, because we know that it's not so critical for us to wait a bit before running. So how to gather all these small tasks on one core? So we must emulate a multi-package topology in order to take advantage of the SCADMC power saving behavior, so that the scheduler will try to gather all the tasks in one package. We need to increase the CPU power, which in fact is describe the CPU capacity, in order to keep all the tasks in one core, even if we have several tasks running simultaneously. And we can use a flag which is called async packing flag in order to use CPU 0 in priority. So this flag ensures that the busy CPU will be the CPU 1 and not another CPU. So the topology can be modified when the SCADMC policies change from the default behavior, which is the performance, to level 0, which need a single package dual core system in order to take advantage of the migration. So we can modify that when we switch to the power saving policy, which is the SCADMC level 2. And for this configuration, we can emulate a single core multi-package topology. Okay. The CPU power can be increased thanks to an architecture-specific function, which is called R-scale frag power. And we can define a scheduler domain configuration for our ARM architecture in order to enable the async pack flag in power saving mode. So all these interfaces are available in the kernel. But to be honest, I'm abusing a bit this interface, and mainly when I'm using the harsh scale FREC interface, in which I'm increasing the CPU power to say, in order to say to the scheduler, this core can run several tasks, which simultaneously, which is not the real case. So I have done all the previous modification and run my cyclic test on the board. And we can see that all the cyclic test threads are running on CPU 0, and my CPU 1 stay idle. So we are quite close to the CPU hotplug behavior, which means that we should have the same power consumption. So if we look at the figures, so I have added some gray column, which are the power consumption with the previous configuration. So on the right chart, we can see that with the regular scheduler in SCADMC power saving level 2 and some modification of the topology and the CPU power, we have a power consumption that is quite close to the CPU plug 1, but still a bit higher. And when we look on the right side of the screen, so the chart shows us that the retention in SCADMC level 2 mode is better than the default behavior, but still a bit lower than the CPU plug. And this can explain the power consumption difference. Now, I have started to study this difference, and when we look at a bigger period, so instead of the few milliseconds before, we have a screenshot for 2 seconds, and in this case, we can see some awakening on CPU 1. Some few one, but we still have some. And these awakening are not cyclic test threads, so there are something else that we need to find and to solve. So why this awakening when we know that the cyclic tests are not the threads that are running on CPU 0? So we have something else that is waking up our CPU, and we need to find that. So one first reason for awakening CPU 1 is the idle load balance, so the ELB. The idle load balance runs on an idle CPU to check the load balance of the system and to pull some task from an overloaded CPU. So the ELB, in fact, so the ELB is triggered as soon as we have more than one task that is in the run queue of a CPU, which is our case, in fact. So this behavior is quite normal when we want to spread all the tasks in all the CPU. But it's not what we want, because we have increased the CPU capacity. So instead of just looking at the number of running tasks in the run queue, we should also compare that with the CPU capacity to say that, OK, this CPU has more capacity than one task, so I don't need to start the idle load balance, because it's not overloaded.
In that case, you have a lot of load on your CPU, so it should be for performance better, even more to have your tasks run on CPU, but also.
No, in fact, they are so small. These tasks are so small that it costs more to wake up CPU 1 to run this task instead of just waiting a bit and run on the same CPU. So this time scale is few milliseconds. We are using cyclic tests, so they are quite small. We have in this screenshot, we have 4 cyclic tests that are waiting for the CPU 0, but they will run something like 100 microseconds, not so more.
So in that case, the CPU 1 is in the WSI.
Yeah.
So
yeah.
Very fast to wake up, and
But we're still consuming more, because we have some. When we compare, in fact, we will have more inter and leave sequence, which cost, even if it's small, because we will not flush a lot of things. This will cost more than just waiting a bit and run on CPU 0. So the main goal of the ELB is to spread this task when we are in performance mode. But in our use case, we see that, and in fact, it's what the CPU plug is doing, just keeping everything on CPU 0. So this is clearly for some small or light CPU load use case. Not as soon as you will have some heavy or mid-range CPU load task, for sure, it's better to wake up the both CPU and to run on both CPU in order to race to the idle. But the CPU load is so small that it's not worth to race to idle, in fact. So as we begin to discuss of the load balance, we are going to continue. And we have other method in order to check the load balancing of the system. So the load balance is checked on an idle CPU, but it's also checked when a CPU becomes idle, a newly idle CPU. So during this, the newly idle CPU will just check the system and verify if it can pull some task on another CPU. And we have also some periodic load balance on the running CPU just to verify that the complete system is well balanced and one CPU has not much more tasks than another one. So like ELB, all these load balance checks are necessary in order to have a well-balanced system. But we don't have this overhead when we are using only one CPU. When CPU 1 is unplugged, we have only one CPU, and in this case, all these load balance checks are not executed. So we have less CPU. We are running less things on the CPU. And when we have a light CPU load use case, this cost can become can become significant. It's no more negligible. So the load balance is based on the CPU capacity. So this CPU capacity is set by the field CPU power. And when a CPU or when the CPU 0 is out of capacity, so when the number of running tasks on CPU 0 is greater than the CPU power, in this case, the idle load balance will pull some tasks on CPU 1, which is normal because we have an overloaded system. And as soon as the CPU 0 has some available capacity, in this case, we will pull back the thread on CPU 0. So when can we migrate a task? So the task migration can be done in three main events, which have been described just before. So the newly idle CPU event. So a newly idle CPU will pull some task. The ELB event can also pull some task on a busy CPU. Or a task can also wake up on a new CPU. Okay? In this case, we will check what is the best target between the previously used CPU and this new CPU, depending of if we have run, if the cache is hot on the previous CPU, if we are sharing or not some CPU, some resources. But what about an isolated task? By isolated task, I mean a task that is fully asynchronous to the tick and that is asynchronous to any other task. So we can, on some idle use case, we can have such kind of task. So in this case, the task will run out of these three possible events, and it will not be possible to migrate this task. So we just maybe, yes, I have not precise that the idle load balance and the periodic check are only done at the tick. So if we have a small task on the tickless configuration, if we have a small task which runs between this tick, we will never trigger any load balance check. and the task will stay on the same CPU. So that can be an issue for us, but we should be able to modify the select task RQFAIR function in order to take into account such use case in which you have only one task running, everything is idle, and we want to use CPU 0 in priority. So the real-time scheduler, so the SCADRT, has no power policy. The tasks have some fixed priority, and the scheduler is just trying to find the best CPU to run the current task, whatever the policy of the CFS, completely fair scheduler, is. So this can break all the effort you are doing to keep everything on to keep the CPU1 idle. Okay. Now, in such low power use case, we should probably be able to pin all these real-time tasks on CPU 0. This can have an impact in their latency, but we should not break their real-time constraint. Just because we are comparing a use case which can run when CPU1 is unplugged, so which means that when we are unplugging CPU1, all these real-time tasks are running on only one CPU. So there is no reason that even if CPU1 is unable, they can stay on CPU 0. So that this issue can probably be solved using cpuset. We have also some deferrable activity which are pinned to the CPU1. So they are created during the CPU up sequence, but they not wake up the system. As deferrable activities, they will just take advantage of another wake up to run. So it's not a problem in itself because they will not generate spurious wake up of CPU1. But if we wake up CPU1, they will run and consume some power, whereas they are not really necessary. So this is an example linked to the timer and high resolution timer. So this framework are using the bus, the timer bus or the high share timer bus of the current CPU when you are starting a timer. So in fact, this is true only if the CPU is not idle. Otherwise, there is a scheduler function that can be called in order to select a busy CPU. But if we look at the screen in our use case, when in fact we have the use case that the timer fire, rearm itself, and wake up a process. So we have the sequence that the cluster is wake up by the broadcast timer. So the CPU 0 is wake up. It will broadcast the timer event to CPU 1 because the timer is pinned on CPU 1. The CPU 1 will rearm itself, but because all the CPU are idle, it will stay on the CPU 1 instead of migrate to CPU 0. It will wake up a task on CPU 0 and then wait for the next period. And because we have wake up CPU 1, all the deferrable activity will run. So this is not optimized for our configuration, but we should be able to modify the get no HZ timer target in order to migrate, to force the migration of this timer on CPU 0. So when we are plugging and unplugging the CPU 1, we have such migration in order to be sure that everything is on CPU 0. So this is feasible. We just need to add this specific use case. So when we run the cyclic test with all the previous modification, so we still have the cyclic test thread which are running on CPU 0, and when we look at a large period, we see that we have no more wake-up activity. So this means that in power-saving mode, it's KLMC power-saving mode, if we have a topology which is single core multi-package, when we have increased the CPU activity, the CPU power, if we are using the asymmetric packing flag, if we are starting the idle load balance only if we are out of capacity, if we migrate the timer and the isolated task on CPU 0, we can reach a configuration or a behavior that is quite similar to CPU plug 0, to CPU plug. Sorry. Now, the question is that when we should gather or when we should spread this task. Because up to now, we have only tried to gather all the tasks in CPU 0. So we have seen that that could be possible. But we don't want to always have this behavior. Sometimes we want to spread. In fact, in all the known light CPU load use case, we want to use all the CPU. So for my study, I have used the p-state and the number of running tasks to choose between spreading or gathering the task in one CPU. So the current p-state helped me to detect this light CPU load mode in order to increase the CPU power and gathering tasks on CPU 0. If I was using another if I were using another p-state, it means that we have a lot of load on my CPU, and in this case, I'm using both CPU. So this policy is not perfect. It was just a small, quite easy to implement policy just to choose between a CPU plug-like behavior and a normal behavior.
Where is it implemented?
In fact, I'm just informed of the frequency change, and I'm updating the CPU, so it's in the kernel, and I'm updating the CPU power according to the current p-state. That's all.
So it's like a driver, or?
Yes, it's like a driver and in which you can add some platform dedicated information to know which p-state for which p-state we should gather the task, and for which p-state we should use the normal behavior.
Why don't you do that in the driver or in the p-state governor?
Because at the end, the p-state might not be the only information that we need.
P-state is already...
It's CPU frag from p-state. Yeah.
P-state is already looking at the number of, not the number of running tasks, but like the load average is quite equivalent to the number of running tasks. So I'm wondering...
Yeah, it's exactly what I'm using. I'm using the CPU frag driver and the on-demand governor to detect a light CPU load use case. A light, yes. And I have registered the callback to the CPU frag transition. So when I'm in the lowest p-state, I'm just running a callback that will update the CPU power.
I was just wondering, you have one p-state for 200 megahertz, another for 400, and
Yeah.
the pattern sees that the
Yeah.
frequency. Could you have another p-state like 200 megahertz and only one CPU? And that could, you could just have changed your p-state driver.
Oh, yeah. But in this case, you have a p-state driver that is not only managing the frequency, but that have to decide if we must use one CPU or two CPU or 3 or 4. But the
Performance driver, it's CPU frag, but p-state is
Yeah.
performance driver.
that can be discussed, but my point was just to keep that separate. We have CPU frag driver that is managing the frequency, and I take advantage of this load monitoring to detect, as an input to choose the CPU power. That's why, just to make that quite simple and different. I think that I need to go a bit quickly. So my policy, at lowest p-state, I increase the CPU power, which increase the capacity of CPU 0, and the load balance will gather everything on CPU 0. For other p-state, I'm decreasing the CPU power, which will decrease the capacity of my CPU, and which will spread all the tasks on both CPU. So this is quite a small test. So I'm running cyclic test, which is gathered on CPU 0. Yeah. And I've run sysbench for a few seconds, and we can see that the CPU 0 become out of capacity because we are increasing the frequency, and the tasks are spread on both CPU. And when sysbench is stopped, everything gathered on CPU 0. So the conclusion, we are quite close to the CPU plug power consumption. So with not all the described modification, but most of, I have done the test of the MP3 playback on my Snowball, and the power consumption is quite close to the CPU plug 1, less than 2%. So we still have some issue to solve, like the isolated task, which must be taken into account in the scheduler. Now, we have also some new mechanisms that are coming that will help us to make a better power-aware scheduling. So we have some patch from Paul Turner, which track the CPU load on a task basis instead of the CPU basis. And last week, we have a discussion with the scheduler maintainer, Peter Zylstra, and a lot of other guys which are active in the scheduling in order to see how we can make the scheduler more efficient from a power saving point of view. So they have agreed that we need to make some modification, some huge modification in the scheduler. So this will come soon, and it's just a starting development. Here are the reference to our wiki page, the Lenovo Power Management wiki page. So the software that I use for my test is available on my Git tree. A web page of the Snowball if you want some information. And I have added the wiki page of cyclic test, which I've used for my test. Also the wiki page of kernel shark, which is the tool that I have used for doing my screenshot. I think that, yeah.
So let's say you have decided that current CPU load in the system,
Yeah.
the system is low.
Yeah.
And you unplug one of the CPUs.
Yeah.
And right after you unplug it, the load of the system has increased.
Yeah.
Now your algorithm says you've got to replug the CPU.
Yeah, so that's why when we are using CPU plugs, that the main use case that we don't want to have. So when we are unplugging a CPU, we don't want to replug it just after. With the scheduler, we are not unplugging the CPU. We are just letting him idle. It means that as soon as new task or a lot of activity is waking up, we can migrate some tasks immediately on this idle CPU. So we don't have to take care of such situation because we can handle that quite quickly, which is not the case with CPU plug.
Right after you unplug it, let's say system load has increased.
Yeah?
Then you got to wake it up, right?
Yeah.
Plug it up. So, but if you have to replug it immediately,
Yeah.
then your trade-offs of time and power may not be judicious anymore. Right?
Yeah.
But that was exactly what he's saying, that hot plugging the CPU is bad, which is why this research into SCADMC and how to do that. With SCADMC, you don't have to hot plug the CPU anymore.
Right? So just put it in.
Yeah. 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 Maybe.
So is this MC in the kernel, or is
Yes.
it something you added?
No, so I'm using SCADMC in the kernel, and I have also, let's say, take advantage of the available interface of this SCADMC, and I have made some few modifications, the one that I've described, but otherwise I have not modified the kernel.
So for instance, this is CPU underscore power. Is there
Yeah.
something that's
Yeah.
other than
Yeah. It's a default field of the scheduler.
Okay. Thanks.
A couple of comments. One, I think, is
Yeah.
done to what he said. Is in a way, it looks like you're asking your scheduler to predict the future in the sense that if you have more than one task that's ready to run,
Yeah.
your scheduler currently brings the second CPU online immediately. What you're really asking the scheduler to do, if this condition persists,
Yeah.
then bring the second CPU online, which I think was what he was saying with the hysteresis and CPU. The other thing that occurred to me earlier in the presentation when we talked about the latency of bringing the second CPU
Yeah.
Does that suggest that the logic thread is not running on the real-time scheduler, and so it's getting prioritized?
No.
Because the latency went from 100
Yeah.
milliseconds to 2.5 seconds on your
Yeah.
thread, and that looks to me like if the logic that's standard there is running in meters.
No, in fact, this increase is, when you look at the CPU up sequence, you have some a generic part and an architecture-dependent one. The architecture part is stable, is always the same. In fact, we are just, when we are waking up a CPU, we are creating thread, and it's only this thread creation which take more and more time because we need to run the case thread daemon on the CPU0. And
but why would that thread not preempt every other thread?
because there are some just CFS threads, some normal threads. So it's just the completely fair scheduler behavior that we have a lot of threads which are waiting for, yeah.
So we talked to the hotplug guy last week, and I think there's some obvious fixes we can do to improve the hotplug.
Yeah.
There's a scheduling. You're not communicating with the scheduler that this thread that you've initiated to bring the second CPU online is special. It needs to run at a higher priority.
Yeah, yeah.
Than Apache or whatever. But overall, I think this is a really interesting question.
So the scheduler folks don't think that hotplug is the right way because it messes up their